Welcome to Tollefson Physics. So today we're going to continue using velocity time graphs to solve problems about motion. And so this is part 2, so be sure to see part 1 and part 3 where we're doing different types of examples. All right, so in this case we're going to focus on things that involve knowing the slope ahead of time and what we can do to solve things. So let's read this first one. So we have an object that's being dropped from a bridge. We time it, takes 3 seconds to hit the ground, and we're going to assume there's no air resistance. So we're going to try to figure out what's the height of the bridge and what is the speed of the object when it hits the ground. So we're going to base all of this on velocity time graphs because velocity time graphs have two very useful properties. The slope of the line is the acceleration, and the area under the curve is the displacement. And so let's draw, I guess, a bridge. So here's a bridge, very bad bridge, right? Got a person there, it's going to drop something, it's going to fall down, it's going to take 3 seconds. All right, and the rate of acceleration, because it's in free fall, we're going to round it to 10 meters per second squared. So now what we can do is let's draw a velocity time graph, because the velocity time graph is going to give us some information that will allow us to solve for the slope and the area. So in this case, it's starting at rest and it speeds up. Speeds up to something we don't know, so I can't put a number there. But if I put a little dotted line there, we do actually know it takes 3 seconds to hit the ground. Now the other thing that we know is the slope of the line is 10 meters per second squared. So I kind of write it as a slope right there. So what we're going to do is we're going to write an equation based upon the slope of the line, right? So just remember from math class that slope is rise over run. But when we're looking at a velocity time graph, we're going to make that more useful because on a velocity time graph, slope is called acceleration, and the rise is the change in velocity, and the run is the change in time. All right, so let's look at the things we know. We know what the slope is, it's 10, and we know what the time is, it's 3 seconds. So it's not a bad idea to go ahead and cross multiply this. So what do I mean? Multiply both sides by t. All right, I'm going to drop the deltas because everything's going back to 0 in this case. And so that final velocity is going to equal the acceleration times the time. So my velocity is going to equal 10 meters per second squared times 3 seconds. And so that is 30 meters per second. Cool. So I now know how fast it's going when it hits the ground. Okay, but the other question was, how high is the bridge, right? And so to figure out how high something is, we're going to look at the area under the curve here. So I'm going to move over here. And so we want to know how big that area is. So the area on a velocity time graph is called displacement. And the shape of this is a triangle. So I'm going to use the idea of 1/2 base times height. Now in this particular case, I actually know the base, so why not write it in this time? So 3 seconds. And then what I want to know is the height. So I didn't actually put in the number for velocity because it's right here. So let's replace that with 30 meters per second. Just 30 meters per second. And so then let's do this math. So when I take 3 times 3, that's 9, with a 0, that's 90, and then divide by 2, that is a distance of 45 meters. All right? So that velocity time graph, once again, super important in doing problem solving in these cases. All right, now let's look at a fan car. So we have a fan car that we're going to release from rest. And it's going to take 4 seconds to travel 8 meters. And this is the kind of data that we'll be taking with the fan car project for those that are doing it. And so I've got my fan car. I guess I could make a fan on it. The velocity equals 0 to start with. It's going to speed up, but this distance is going to be 8 meters, and it's going to take 4 seconds. And so then it's over here somewhere traveling at some speed. So once again, let's start with the velocity time graph. This is another case of speeding up. So I'm going to draw something that starts at rest and it goes up. I do know the time because I had a stopwatch. So it's 4 seconds. And I know the distance. So distance is the area under the curve. And so because I know the distance, that's a good starting place for my problem solving, is to think about what the area tells us, right? So the area of the triangle is 1/2 base times height. So from a physics standpoint, which I didn't write on the last slide, right, is area is the displacement. We're using the idea of the area of a triangle, so it's 1/2, the base is time, the height is velocity. So we want to know, what can we figure out? Well, we know the distance and we know the time, so we can figure out that final speed. We can rearrange this equation, multiply both sides by 2 and divide both sides by t, and it gets rearranged to 2x, and I'm going to remove the delta because we're starting at position equals 0, divided by t. And then when we put in the values that are given to us, we have 2 times 8, which is 16, divided by 4 seconds, and so that gives me 4 meters per second. The other question that I want to answer is, well, what is the acceleration? So the acceleration is the rise over the run. So in this particular case, we just figured out the rise is 4 meters per second and that the run is also 4 seconds. So in this particular case, the acceleration is 1 meter per second squared. All right, now it's your turn. So I want you to try this question before you look at what the answer is. So we have a world-class runner, and actually this was modeled after a world record. You can only accelerate for a short amount of time in a race. So this is from a 100-meter race. They're not going to travel 100 meters in the first 2 seconds. But that's where the highest acceleration is. So we're going to make the assumption they're starting at rest, and then in the first 2 seconds of the race, they can accelerate at a rate of 3 meters per second squared. So what I want you to figure out is, well, what is the runner's speed after 2 seconds, and what is the distance that they travel? So pause the video here, and then when you're ready, come back and let's see what the answer is. All right, so we have this runner starting with no speed, and just for the first 2 seconds they have an acceleration of 3 meters per second squared, right? So then at this point over here they're running and they have some sort of final speed. So velocity time graph, right? So velocity time graph. Velocity time, I do know it's 2 seconds, so I might as well throw that on the graph now, and we're going to assume a constant or uniform acceleration. We know the slope is 3 meters per second squared. So since we know the slope, that's a good place to start since I don't know the area. So I'm going to go with the slope first, which is kind of the theme of this video. And so the slope is the rise over run. So once again, acceleration is what the slope means. The rise is the change in velocity, and the run is the change in time. So now if I this time I'll substitute numbers instead of rearranging. And so it's 3 meters per second squared is that change in velocity, and I'm going from 0 to something, and it took me 2 seconds. So multiply both sides by 2, and that final velocity, since the starting velocity was 0, is 6 meters per second. So how much ground did they cover? So this is a typical acceleration at the beginning of a 100-meter race. So how far did they go? And so that's what area is. And so once again, right, area means displacement. The shape is a triangle, so 1/2 base times height. Well, I was given the base, and now I know the height, so I can actually solve for this now. So 1/2, the time is 2 seconds, and the height is 6 meters per second. Well, 2 divided by 2 is 1, and so the distance traveled, this isn't very far, right? The distance traveled in those first 2 seconds is only 6 meters. All right. Typically what ends up happening is they'll go kind of at a constant velocity and then start to slow down as the race goes on. So this is a quick burst of speed, and then the race changes a little bit because the way physiology works. Anyway, so these are, every single one of these problems is involving looking at the area of a velocity time graph and looking at the slope of the velocity time graph. And it's helping us be able to solve things about it. So hopefully this helped. Make sure that you, if you haven't, look at part 1, and then definitely stay tuned for part 3, which deals with, I don't know the velocity and I don't know the time. So how do I solve it using this method? All right, good luck to you.